So let's come back. So because someone comes a little bit late, so let me rephrase again. So actually, the attendance topics introduced today will not be in your final. Okay, so yep. Okay, let's keep going on this one. So the thing is, like, if in a synchronous I/O systems, actually there are some process the working set will be kicked out, because if there are a lot of processes that are executing together, for example, P1, P2, P3, and P4, and then P4 is possible to evict the P1 process working set. So we run an experiment on Linux and then to run several processes in a round robin way. So actually, you can find like for each process, sorry. Okay, so you can see like actually the blue one is the asynchronous, and then the y-axis shows the stored memory access. So stored memory access you can think about just like swapping or like the patch flow, and then the x-axis shows the timeline. So for the asynchronous, for using the asynchronous I/O, most of the time the slow memory access is stable. And the reason is about because each time if there is a patch flow and then they switch to another process, so usually there is no working set contention issues here. Okay, but the thing is like if you are using the synchronous I/O, actually the slow memory access it fluctuates a lot. I mean sometimes it will be super low. Super low means like there's very few patch flow, and sometimes it's super high. So super low, the reason for super low is because if this is a too intensive process, and this process, if it doesn't really need to get data, too much of data from storage device, then even there's one or two context switch, it will not be switched out. So you can enjoy the time, the whole time slice for a CPU. So it will be super low. But super high means like, for example, in this scenario, because P1 kicks out all the P1's working set. So P1 needs the time to reconstruct its working set. So working set reconstruction means to move a lot of data from storage device to memory. So actually you can see like there are several peaks here. It's about the time like some process is going to reconstructing the patches. Okay. So actually like our solution is about an adaptive synchronous patch flow handler, and there are three main parts. The first one is about immediate synchronous patch prefetching. Sorry. So it's going to prefetch patches by considering patch access behaviors. Okay, and the second one is about adaptive CPU scheduling. So we try to slightly modify the CFS to support this kind of synchronous patch flow scenario. And the last one would be the asynchronous patch prefetching. Okay, so there are two prefetching. The reason is about if during the patch flow, we are going to move some data, then if there are not too much of data, for example, if you still remember the evaluation, like, one moment. Here, if you still remember, actually, 32 kilobyte works better than 4 kilobyte. So it means like if it is possible to prefetch very few patches at the same time, for example, like 2 or 3 patches at the same times, we can get better system times. Okay, so this is the reason why in the synchronous we were doing, sorry, in the synchronous I/O times we will do the prefetching. And then for the asynchronous means when one process is going to do the context switch to switch in another process, we will do a thing called asynchronous patch prefetching. So asynchronous patch prefetching is about because context switch takes time, right? So why not just prefetch more data? Or like you can think about why not just do the working set reconstruction at this time? Okay, so for immediate synchronous patch prefetching, I think it's quite naive. So I will quickly go through it. Just like the main idea is about if there are several patches, they are accessed at a very near time slice. I mean, if there are temporal locality, then we will modify some Linux data structure to to record this scenario. Okay, so you can think about if patch A and patch B, they are accessed in a very similar time, like patch A, patch failed, and then after that, patch B also patch failed. So it means like patch A and patch B, they are accessed in a very near time state. Then we will set them in the same set. This is called set K, or you can think about group K. So if patch A is already in group 1 or like set 1, and then after dealing with patch A's patch fault and patch B also have the patch fault later, then because they are in a very close time, so with the locality considerations, patch B will be allocated to the same group as patch A. So now patch A and patch B, they are all in the same group. So actually, when we are doing a synchronous patch prefetching, we'll prefetch all the patches in the same group. Okay. So for example, now patch A and patch B, they are all in group K. And now patch A faces a patch fault. And at the same time, we'll prefetch patch B. So in this scenario, if during the patch fault, patch A here, and we have a patch fault, and we do the prefetch, and we prefetch patch A and patch B together, then patch B will not occur, will not lead to the patch fault later. Okay. So the second solution is about the adaptive CPU scheduling. So actually, this idea is quite simple. Just like we only slightly modify the CFS. So the reason why we're going to modify CFS is because actually in current systems, they are usually memory intensive and non-memory intensive tasks. So for example, like if now you are using, for example, the Spark systems, for example, and for Spark systems, sometimes it will be non-memory intensive because Spark system is now processing the log now. For example, we are doing to processing some log, these kind of things, then this will be a non-memory intensive task. But if the Spark system is going to run some memory intensive algorithm in the front end, then this will be memory intensive. So it depends on what kind of things you are running. Then in the same systems, in different time, they are running non-memory or memory intensive tasks. So we are going to let the CFS aware of this kind of design. So the thing is like this. If now we are going to insert a memory intensive task into our CFS tree, because CFS you already know, so let me just skip the introduction on CFS. So without adjustment, the new memory intensive task will be inserted at the tail of like here, H, right? Because we say like for those processes on the left-hand side that needs CPU more, and usually memory intensive test is not that high priority task. So usually it will be at the tail of the tree. Okay, so this is the traditional without adjustment. So without adjustment, like we will insert the I between one non-memory intensive task. So you can see it would be like this, H, A, I. Okay. So what's the reason here? So the reason here is because we don't want to let two memory intensive programs to schedule together. In this case, two memory intensive tasks will kick out too much of memory. So it will make the working set contention becomes super serious if you're going to schedule these two memory intensive tasks together. So a better way is about we will use one non-memory intensive task to alleviate the working set attention issue. What do I mean? So when you schedule, when the schedule sequence is memory intensive, non-memory intensive, and then the memory intensive, okay. So when you are running H, right, you will kick out a lot of patches. And then when you are running A, because A is non-memory intensive task, so usually it doesn't really need to move too much of data in the memory. And it means CPU can just go for the process progress for process A. And at the background, we can use DMA to preload the booking set belonging to process I, right? Because process I is a memory intensive task. So in most cases, most of the working set, they are kicked out by other process because it occupies too much of the memory. So when CPU is running process A, at the background, CPU can configure DMA to rebuild the working set of the next memory intensive process called I. So if we schedule one non-memory intensive process between two memory intensive process, then we can not only alleviate the working set attention, we can also trigger the working set reconstruction for the memory intensive process. Okay, so we can leverage the CPU and the DMA at the same times. Okay, so this is just briefly talking about things, so I will skip the algorithm part. Okay, so the thing is about, but how do we know how to do the construction? So we say when we are running process A, right? And we know the next one is process I. And because process A is not memory intensive, so we can do the working set reconstruction, right? But how do we know how to reconstruct I's working set? So we slightly modify some design inside Linux to mark the patch which are accessed previously. Okay, so actually we construct a things called the reconstruct this, and the reconstruct list is very similar to in current Linux is very similar to the inactive list. And the thing is about we will record about the access bit, about it is access or not. So access bit is about if one patch is access, then its access bit will be set by the CPU. Okay, but this is only one bit. So no matter the patch is access 1 or 2 or even 3 times, the access bit will only be set 1 times. Okay, so we use this access bit to know about what kind of patches we are going to recover for the following memory intensive process. Okay, so evaluation, just give it. And the last one will be the how to steal the CPU I/O time when synchronous I/O mode becomes promising. So this is also another synchronous I/O mode research. And okay. So the thing is like this. This is a synchronous I/O. So a synchronous I/O or current operation just designed like this. So there is a context switch occurs when we are going to serve for the I/O device, right? But we say if now the I/O device is ultra low latency device, so the response time is super low, right? So context switch take more time. Okay, so Intel and IBM they are saying if in this case why not just let in CPU busy waiting because storage device is so fast than context switch. But the problem is about when CPU doing busy waiting. Actually, this is still a storage device, so CPU needs to wait for like 2 or 3 microseconds. Then CPU utilization will be decreased. So our idea is about: is it possible to let the CPU run some very special tasks during this I/O completion duration? So actually, the thing is about we cannot run the process progress, right? Because this process is waiting for the I/O, but we still can run some kernel thread. We still can run some kernel function. But what kind of kernel function we are going to run? Okay, so this work is going to explain. Okay, so before that, we are going to know how much of time the CPU spend on busy waiting. So like this. So the x-axis means the number of processes. So we run 2, 3, 4, 5, and 5 processes simultaneously, and the y-axis is the normalized execution time. So we normalize to the two process scenario. So we do the analysis from non-idle time and idle time. So idle time is CPU busy waiting for the storage I/O. So you can see like actually, no matter how many processes you are running, actually the idle time is still there. I mean, sometimes people were thinking about maybe if you run more process, then the idle time can be alleviated because you can hide the idle time. But no, actually idle time is still there. So idle time takes around 30% of the overall execution time. Then how to leverage this 30% of this idle time? Okay. Okay. So our design is called ITS. The idle time still in design here. So the implementation detail is we design different kernel threads to help on the execution progress of process with different priorities. So first of all, when the process is running, and each time the CPU will run an MMU to do the translation for each instruction, right? So when we find like, hey, actually the data is in the store device or in the memory device, actually CPU will store here to wait for the data from DRAM or like store device now. Okay. And if the data is in the store device, we call it patch flow. So there will be a patch flow handler. So the patch flow handler, we do several things, the patch full area checking and patch swapping things. Okay. And the last step, actually, we don't run the context switch immediately because now we know we are not using a super fast storage device. So running context switch is not a good choice. So what we are running is a thing called a priority aware thread selection function. So there are two different steps of the process, high priority process and low priority process, right? So for low priority process, what we are running is a thing called self-sacrificing kernel thread. So self-sacrificing kernel thread is about if this is a low priority process, then actually we don't really use up all the time slice because the system now is using a synchronous I/O. So if the low priority process uses same time slice, just like it being allocated, then maybe it will affect the high priority process. So for the low priority process, we will directly do the context switch if this is a low priority process. Okay. But now, if for another process it is a high priority, then we will not do the context switch. We will run another thing called self-improving kernel thread. So there are several things that we can do in the self-improving kernel thread. The first one is the patch prefetching. Okay, because when doing a patch prefetching, actually it doesn't really affect the process progress, right? Because most of things there are operating system and CPU power stuff there. And then we will run a pre-execution function. But today we will not cover this one because this one is a little bit tricky. There's a little bit related to architecture. Okay, so the design concept behind a self-sacrificing kernel thread is about when a low priority process is waiting for the I/O completions, then we will directly give up this CPU resource to other process, for example, for other high priority process. So it looks more like these kind of things. For a high priority process, actually, when the process execution face the I/O, then we will jump into a kernel and then to run a self-improving. Actually, we need to wait for a lot of time because the data is still in the store device. So we need to wait for the I/O completion. And in this duration between I/O request and I/O completion, the user space cannot run anything. Okay. So after I/O completion or after the data is moved back to the DRAM, CPU can keep executing the process. So it can execute until the timeout. Okay, and then it calls the context switch. So this is for the high priority process. But for the low priority process, it looks more like this. When process execution face the I/O, and because facing I/O, we will not do the context switch in the synchronous I/O mode. But this is a low priority process. If we do the same things as a high priority process, maybe we will affect the progress for high priority process. So why not just do the context switch here? Why not just give up the CPU resource to other? Maybe we can boost the high priority process. So actually, the design rationale behind sacrificing low priority process is short-term sacrifice but long-term benefit. Why we say like this is a short-term sacrifice but long-term benefit? Because low priority process seem to sacrifice their progress, but it can receive more dedicated resource after the completion of high priority process. What do I mean? If there are high priority process and low priority process here, and if each time low priority process give up the CPU resource when it faces the I/O, then high priority process can get the resource more frequent than without giving up the low priority process CPU. So in this case, high priority process can have better chance and have higher chance to finish their task earlier. So if high priority process, if most of the high priority process finish earlier, then when the low priority process is executing, they can get longer execution time. Okay, So this is the reason why we say short-term sacrifice but long-term benefit here. Okay, so I think maybe I need to let the TA to take over now, and then yeah, if we still have sometimes in the rest of this lecture, we can talk about the rest of it.